In this lesson, we're going to cover Unit 9, Acquisition 4 on enthalpy, entropy, and Gibbs free energy. So we've already talked about enthalpy, so we're just going to skip over that for now. We will come back to it once we get to the calculations. First thing I want to talk about is entropy. Entropy is a measure of the tendency for energy to disperse. What that kind of means is entropy reflects the degree of disorder with particles that carry the energy. So we're going to talk about entropy a little bit more, but this brings us to the second law of thermodynamics. The second law of thermodynamics states that the universe is constantly increasing disorder. And the greater the disorder, the larger the entropy. When we're just looking at our states of matter, entropy increases as a substance changes from a solid to a liquid to a gas. Gases have greater entropy because they're more disordered than solids. The way that we're going to calculate entropy, we use the letter S to represent entropy. It's going to look very similar to our calculation for enthalpy. We are going to take the sum of the products multiplied by the number of moles and subtract the reactants. So again, the funky looking E is the Greek letter sigma. Sigma means the sum of, and represents the number of moles. So we'll take the entropy of the product, first product, multiplied by the number of moles, add it to the next product, and so on. So let's look at an example calculation for entropy. All right, calculate the entropy for the following reaction. Nitrogen plus hydrogen produces 2 moles of ammonia. Units joules per mole times Kelvin. And again, you would be given this data. All right, so we're going to calculate this the same way we calculated delta H. We are going to start by calculating the entropy of the products. And again, this is the entropy per 1 mole of a substance. I have 2 moles. So I'm going to do 2 times my delta S for ammonia. Plug that into my calculator, and I would get 385. Moles times moles are going to cancel, joules per Kelvin. Now we can calculate delta S for the reactants, left side of the arrow. Only 1 mole of nitrogen, so 1 times delta S for nitrogen. And again, it is the sum of, so I'm going to add it. I need to multiply delta S of hydrogen by 3 because it has a coefficient of 3. (583.3 joules per Kelvin. And then lastly, to get delta S of the reaction, products minus reactants. 385 minus 583.3 would give me a negative 198.3 joules per Kelvin. So again, the equation, the math, it is essentially the same as our enthalpy. I'm just doing it with entropy. Again, you can do the entire reaction in like one big long step. If you are, be mindful of your order of operations. Be careful to use parentheses. Biggest mistake I see with students who want to do the math all in one big calculation is we're forgetting parentheses, or we drop a negative or something along those lines. Next, we're going to talk about Gibbs free energy. Gibbs free energy is just defined as the energy associated with a chemical reaction to do work. So whether a chemical reaction does work or not comes down to what we call spontaneous process. If a reaction is a spontaneous process, this is defined as a physical or chemical change that occurs without outside intervention. So an example of something that is spontaneous would be like an iron object that rusts when it's exposed to moisture, or ice melting at room temperature. Those both occur without any outside intervention. They're just going to happen on their own, so that is considered spontaneous. The way we tell if a reaction is spontaneous is based on our value once we calculate Gibbs free energy. Spontaneous reaction, delta G is negative. If it takes energy, if the reaction has to do work, it is going to be called non-spontaneous. This reaction takes work, it requires outside intervention. Gibbs energy is going to be positive. The way that we calculate Gibbs free energy is by combining a few things together. Gibbs energy is going to be delta G. Delta G is equal to delta H minus T times delta S. So we're only going to do one example problem, and it's going to put all of this stuff together. So this will be a long problem. So for the following reaction, at 25 degrees Celsius, solid barium oxide plus carbon dioxide gas produces barium carbonate. 4 questions you're going to answer, and I'm going to give you a data table so we can answer them. First, calculate enthalpy. B, calculate entropy. C, calculate Gibbs free energy. D, determine if the reaction is spontaneous. All right, and we're going to have a data table. So I was kind of running out of room, but our units are there. Delta H kilojoules per mole, delta S joules per mole times Kelvin. Sorry, it's a little bit hard to see. All right, you should be able to do A and B by yourself. So A, go ahead and calculate delta H. Delta H of the products, I only have one of them, no coefficient. Delta H of the reactants. Again, all of my coefficients are 1, but I still need to do the sum of my reactants. negative 947. Delta H is equal to products minus reactants. Negative 269.3 kilojoules. B, let's calculate delta S. Again, everything has a coefficient of 1, so we don't have to multiply it. My product, barium carbonate, has an entropy of a positive 112.1. I'm going to take the sum of the reactants from my data table, 70.42 plus 213.6. $284.02. And again, the equation is going to be products minus reactants. Negative 171.92. Remember, moles will cancel, and I'm going to be left with joules per Kelvin. We want to convert from joules to kilojoules. Notice that enthalpy is in kilojoules, so we want entropy to be in kilojoules. And the way that we're going to do this is to set up a little conversion. In 1 kilojoule, there are 1,000 joules. So if I have negative 171.92 joules per Kelvin, going back to conversions like stoichiometry, always set up your units so they cancel. So 1,000 joules will go in the denominator per every 1 kilojoule. So multiply by 1, divide by 1,000, I would get negative 0.17192. Joules will cancel out. Kilojoules per Kelvin. This will be really important once we get to Gibbs energy. We need to make sure that our enthalpy and our entropy have the same units. Next, notice that this reaction is performed at 25 degrees Celsius, but my temperature is in Kelvin. So we are going to convert from degrees Celsius to Kelvin by adding 273. 0 degrees Celsius equals 273 Kelvin. So I'm going to take my 25 degrees Celsius plus 273. My temperature would be 298 Kelvin. Kelvin is a unit of temperature. It does not have a degree sign. The two biggest mistakes that students make: 1, not converting entropy to kilojoules, and number 2, we want to plug in 25 degrees Celsius instead of converting to Kelvin. C, we're going to calculate Gibbs free energy. Our equation, delta G is equal to delta H minus T times delta S. Let's plug in what we know. Negative 269.3 kilojoules minus 298 Kelvin times negative 0.17192 kilojoules per Kelvin. So now we can go through and solve. Delta G is equal to a negative 218.1. Kilojoule over kilojoule will cancel. I'm sorry, Kelvin over Kelvin will cancel. We're going to be left with kilojoules. So Gibbs free energy is equal to a negative 218.1 kilojoules. D, determine whether this reaction is spontaneous. Yes, this reaction is spontaneous. And the reason that we know this reaction is spontaneous is because delta G is negative.